Hello, good morning, good afternoon, good evening, everybody, wherever it might be. It is my great pleasure to welcome MARIUSZ TOBOLSKI, who is my mathematical descendant, and I'm delighted to have him giving a talk about the Stone von Neumann theorem for locally compact quantum groups. MARIUSZ, the floor is yours. You are a new academic year opener. The best of lucks. Go ahead.
Thank you, Piotr. It's always great to give a talk at the Noncommutative Geometry seminar at IMPAN, this time at CISA online all over the world. It's always great to be back at this seminar. So I'm going to talk about the Stone von Neumann theorem. It's based on joint work with Lucas Hall, Leonard Huang, and Jacek Krajczuk. However, the disclaimer for if my co-workers are on this, will hear this talk, this will not look too familiar to them, because you can look at this topic of locally compact quantum groups. That's the first thing, is that you can look at it from two perspectives at least. So either von Neumann algebras, you start with von Neumann algebras, or you start with C-star algebras, multiplicative unitaries and stuff. So one approach is by Kustermans and Vaz, and the other one is by Voronovich. And I will follow the Voronovich approach, or even to go even further back to the approach by Bash and Skandalis. So and in the paper that I work on, we are doing the Kusterman-Vaz approach. So that was the disclaimer for my co-authors. But now let's start the talk. Everything works, I guess. So yeah, so I'll start with the original Stone von Neumann theorem that goes back to Stone and von Neumann. I'll talk about motivation and a generalization by Mackey when he realized that this is actually a theorem about. So you start with quantum mechanics. We start with physics. That's where Stone and von Neumann got their motivation, and the result was about quantum mechanics at first, but then Mackey's realized that this is actually a theorem about certain representations of locally compact abelian groups, right? And then we will go to locally compact quantum groups, and I'll talk, if you're not familiar with locally compact quantum groups, I'll talk a little bit about motivation of this topic, and I will go through all the definitions very carefully. And then we'll talk about the most important ingredients in this theorem, so representations of locally compact quantum groups, and then a universal dual, full cross product, and in the end, I will state that the Stone von Neumann theorem for locally compact quantum groups, not all of them, it will turn out to be true for groups that are called strongly regular. And you'll see during the talk what I mean by that. Okay, so that's the plan, and let me start. So the motivation for the Stone von Neumann theorem is, of course, as I mentioned, quantum mechanics. So we'll go very far back, and the first part will not be very rigorous. I just want to state the most important things, the most exciting things. So it all starts with the canonical commutation relation in quantum mechanics. Right, so as non-commutative geometers, because we're talking about in non-commutative geometry seminar, so we love everything non-commutative, and this is basically the origins of non-commutative geometry and in quantum mechanics. This relation where Heisenberg noticed that this non-commutative relation is true, and then it was the whole study by Born and Jordan was then much like a further study of this, and it was called actually quantum relation at first, right? And then there was the other founding father of quantum mechanics, Schrodinger, had his own approach, wave mechanics, where he talks about operators, and here, for just the sake of the argument, I just write the operators on L2 of the real numbers, just one dimension, right? So it turns out that if you write down those two operators, one is just multiplication and the other one is differentiation, and then you multiply by the minus I factor, you get exactly that these two operators satisfy this commutation relation. So,
Mariusz, just a stupid question. Do I
Sure.
remember correctly that Born, in his book, used the term matrix mechanics for quantum mechanics?
yes, exactly. Yeah. So that was the so Heisenberg reinvented matrices, right? And then Born and Jordan, who already knew about matrices, just used this language to talk about. Well, the question was the spectrum of the hydrogen atom, right? So that was the question there. And so okay, so we had those two papers that started quantum mechanics, one by Heisenberg and the other one by Schrodinger, and everyone suspected that they are equivalent in the end, right? And Schrodinger even wrote a proof of this equivalence. However, his proof wasn't entirely rigorous, right? Because here we talk about operators that are unbounded, and you have to take care about their domains, right? And that was lacking in the approach of Schrodinger. However, if you want to forget about unbounded operators in this context, you can look at this canonical commutation relations in a Weil form. So that was first discovered by Weil. Right? So instead of writing down this equation, you write down this for two unitary. So these are just two one parameter groups of unitary operators, right? You write down those one parameter groups of unitaries, and this equation becomes this here. Okay, and we so this is the way to look at it from the bounded operators perspective. And then as von Neumann was able to prove that the two are actually equivalent. And let me state the Stone-von Neumann theorem, which just is now, instead of just one dimension, I have n dimensions here. So the Stone-von Neumann theorem tells you the following thing. You take a pair of unitary representations of Rn on a Hilbert space such that they satisfy the Weil canonical commutation relation, right? So the same thing that we had before, but now, well, we have more degrees of freedom, as physicists would say. So instead of just multiplication, we have a inner product in Rn here. Okay. So we take a pair of representations that satisfy this, and there's one particular representation that also satisfies this relation, but this would be the Schrodinger. So when we look at this relation, we think about Heisenberg approach and the canonical commutation relation. And then here in this, these two representations that I called mod and rho, one of them you can see is simply just the right regular representation. If we think of Rn as its group structure, the additive group structure. And the other one is just multiplying by this factor. Okay, so we have those two representations. And first of all, you can check that they satisfy the Weil canonical commutation relations because they are nothing else than just integration, or well, just this not integrated, sorry for that. These are just exponentiated operators from before this x and p. That's what you get when you exponentiate. And every such pair that we had, so any pair of unitary representations of Rn that satisfies this are just a multiple of this one representation. And here should be rho, so there's a typo. So here should be rho instead of lambda. So basically this just tells you that if you have any representation, any pair of representation of Rn of Hilbert space that satisfies this Weil canonical commutation relation, it is a direct sum of this one pair of representations. Right? So this basically tells you that it is enough to study the Schrodinger representation if you want to talk about quantum mechanics. And that's why on Wikipedia pages, you only see, let's say, quantum mechanics in this, you only talk about wave functions and the Schrodinger equation. Well, that's basically why, because if you have any other representation, it's only a direct sum of this fundamental representation, the Schrodinger representation. Okay, so that's this original Stone-von Neumann theorem, but let me go to things that are more general and that, because so one thing that you can notice if you take those two representations, that Rn as a group with this additive structure is self-dual in the sense that its Pontryagin dual is again Rn. So Mackey's idea is that this theorem maybe is not exactly about pair of representation of Rn, but maybe a pair of representation of the dual group and of the group itself. So now let G be a locally compact abelian group. G hat is its Pontryagin dual. And again, we're working on the Hilbert space. Then, and this would be it's not the exact formulation of Mackey's theorem generalization that you can find in Mackey's paper, but this is just, to how we can now nicely formulate it. And this is the exact same way that I want to generalize it to locally compact quantum groups. So now a Heisenberg G hat G representation is a pair, but now I take a unitary representation of the dual group and then the representation of the group, and I ask them to satisfy this commutation relation, right? When here this chi on G is just the pairing of the character on the group, right? So this is what Mackey just saw in this relation, that this is the relation you want to look at. And then the Schrodinger representation is exactly this pair. It's again the same as this pair mod and rho. I denoted the same way because one is the right regular representation, right? So we just multiply by G here, and the other one is just you multiply by the character. Okay. So now, first, of course, you can check that these two representation fit into this definition of a Heisenberg G hat G representation. So you get this Weil canonical commutation relation. And the theorem is the same, that any Heisenberg G hat G representation is actually a multiple of the Schrodinger representations, right? In the sense that it's a direct sum. And now the proof of the modern proof of the theorem goes as follows. I'll only give you that sketch of the proof, just the idea, how it goes. So first of all, you notice that there's a one-to-one correspondence between Heisenberg G hat G representations on H and non-degenerate star representation of the full cross-product algebra. Right now we're talking about C-star algebra. So this is the full cross-product. I have an action of G acting on the C-star algebra of functions on G vanishing at infinity, right? And I create the full cross product. And then it turns out that those Heisenberg representations are exactly in one-to-one correspondence with, so this Weil commutation relation is, because first, if we look at the star representation of the full cross product, right, they are in one-to-one correspondence with covariant representation on dynamical system, which are pairs. So one, we take a representation of G, okay, so that's in your Heisenberg representation already, and then we take a star representation of C0 of G, but star representations, non-degenerate star representation of C0 of G are just in one-to-one correspondence with unitary representations of G hat, right? So that's how you get your one from the other. Well, that's just the idea. And then you realize that the fact that these two form a covariant representation is just the same as this Weil commutation relation. And that's the whole proof, basically, of this, how to show this one-to-one correspondence between Heisenberg G hat G representations and non-degenerate star representations of full cross product. And then, if you know this, you can invoke a theorem that this cross product is basically isomorphic to the compact operators on L2 of G. Okay, and this follows from either Green's imprimativity theorem or Takesaki-Takai duality, right? Which these are two theorems that are more general than what I'm stating here, of course. But if you know that this C-star algebra is just compact operators, then you can use your knowledge of compact operators and the representation there, and you know that all representations are just direct sums or of irreducible ones, right? And
sorry, this is a plain isomorphism or only Morita equivalence?
No, this is isomorphism.
Okay. Okay, thank you.
So so that's the theorem, and basically so the whole idea of the proof is to use the fact that what we know about compact operators to get the result. Okay, so that's the Mackey generalization of this theorem. And at this stage, you can generalize it in various ways. You can, for example, you can go from Hilbert's. Here we talk only about representations on Hilbert spaces, right? So you can go to Hilbert modules over C-star algebras, but not any C-star algebra, because you want to reduce the problem in the end to representations of compact operators. So you look at elementary C-star algebras on which the group that you work with acts. And then you can generalize Mackey theorem this way. And this is what was done by two of my collaborators, Lucas Hall and Leonard Huang. That's what they did, that they generalized Mackey's theorem in this way. But still the group there was abelian, locally compact abelian group, so the classical group. And the kind of like an anecdote or a funny thing that basically this project started on Facebook, because Leonard just posted that he had this new paper. He posted it on Facebook, and I just replied, well, let's do it for quantum groups. And yeah, that's how this project started. So that was one of the instances when Facebook actually turned out to be useful. Okay. So now I want to, so the whole idea of this talk is to look at Mackey's theorem and at this proof and try to generalize it step by step. Okay, so and my main motivation for this, just to be honest with you, was I finally wanted to learn locally compact quantum groups. Because when I was doing my PhD, I was using quantum groups a lot, but only the compact quantum groups, right? And this world of locally compact quantum groups was still terrifying for me, and I was not brave enough to enter that realm. But you know, after I was already a PhD, I decided maybe it's time to learn this stuff, because it was always fascinating for me. So that was my main motivation, and the best way to learn stuff is through problem solving. So I thought, if I can do this theorem, and my impression was that this should have been done long time ago, but well, if you have a reference that you can point me to, I'll be happy to acknowledge that, but I couldn't find one, so that's why we're working on that project. Okay, so what's the motivation to work on locally compact quantum groups if you never heard about them? So first of all,
I have a question.
Yep.
So how does this ability, the commutativity, play a role
here? If you want to define the Pontryagin dual, right?
Yes,
you need your locally compact group to be abelian.
What's the counterpart? I think these abelian groups play in a crucial role in this case. You can use this basically this Pontryagin duality. How does it play? So what's the counterpart in the quantum group set? Or like within that?
Yeah, we'll get to that. No worry. So if you give me some more time, I'll talk about quantum groups and what's the counterpart of the Pontryagin duality. Okay. Any more questions?
I don't see any raised hands. Oh, go ahead.
Okay, so we started talking about Pontryagin duality, and this is something that is we have this beautiful theory and this beautiful result for locally compact abelian groups, right, that is connected to Fourier analysis and many harmonic analysis and many great things in mathematics. And the idea of locally compact quantum groups, at least for me, it was when I was trying to learn about them was that if you want to go to non-abelian groups, right, what can you find there? What would be the good analog of Pontryagin dual? And well, the first idea is to just, well, okay, so instead of what we do for abelian groups, like we look at representations. But if your group is abelian, and then you still for the group of for the characters, you can still write down the nice group structure, and you get that from you start with a locally compact abelian group, and you get again a locally compact abelian group. Of course, I'm talking about Hausdorff spaces here all the time. I'm assuming that these are locally compact Hausdorff groups all the time. But if your group is non-abelian, then there's no good way of putting group structure on the space of unitary representations. Okay, so one way to look at it, and that was the beginning, would be to look at group algebras, right, instead, and at representations of group algebras, which in the abelian case which also correspond to so your representations of group algebras correspond to representations of groups, right? And then if you look at it from the noncommutative geometry perspective, if you have a non-abelian group, your group C-star algebra is also non-commutative. Okay, so then Gelfand-Nijmark theorem tells you that for all locally compact Hausdorff spaces, right, we have the correspondence, the anti-equivalence of locally compact Hausdorff spaces and commutative C-star algebras. And when the C-star algebra is non-commutative, then we have this philosophy of still we look at it as C-star algebra of functions on a non-commutative space, which now would correspond to this dual group. Okay, so locally compact quantum groups form a category that is closed under this generalized Pontryagin duality, which I will define. Right, so that's the main motivation for locally compact quantum groups, that you can define a category in which you can have this generalized Pontryagin duality. And what even more exciting and motivating is that there are many examples that are much different than the ones coming from actual groups. And that was already in the case of, let's say, compact quantum groups like the Voronovich SUQ2. So this is the motivation for locally compact quantum groups. And now let me go to actual definitions. And I said at the very beginning that I'll go even further. I'll talk about the approach of Bash and Scandalis. And this is how they define locally compact quantum group. And then I will only vaguely mention the generalization by Voronovich, because in this talk we can focus on groups given by the multiplicative unitaries defined by Bash and Scandalis. So now I will assume, just for safety, because it's still a new ground for me, so just for safety I'll assume that the Hilbert space is separable, and from now on you can just assume it. If you don't want to assume it, I was not going into technical details what will happen if the Hilbert space is not separable. But just for the sake of the talk, let's assume that we work on a separable Hilbert space. And then I take a unitary operator on H tensor H, and it's called a multiplicative unitary if it satisfies the so-called pentagonal equation. So that's the equation, right? And in this equation, I use the Lac Numbering Notation, which is defined as follows. So W12 is just that on the third leg, I have the identity, and here W23 is that on the first leg I have, because what? W12, so here this equation is in bounded operators on the H tensor H. So I have three tensorons here, right? So I want this is an equation on, well, with three legs, let's say, right? And this is how this notation works. And this is the most troublesome one, right? Because I have to somehow have the identity only on the second leg, and this is how it's done. I use this flip operator, which just flips the elements in the tensor product. All right, and I is the identity operator. So this is a multiplicative unitary if I have this equation. And then it's called regular, and that's the definition of Paschen-Skandalis, if the following is satisfied. So if I take the span of elements of this form, so first I take the flip operator on W, and then I slice it with the use of, so here B of H star is the set of all normal linear functionals. So I slice it with those linear functionals, and the span of the elements of this form has to be the compact operators on H. And here you already can see that this kind of, I need this kind of relations to go to the Mackey's theorem and to go to, let's say, Takai duality. So this regularity will, or even a stronger property of strong regularity, will play a crucial role in that generalization.
Okay, may I have a question?
Sure.
So usually it turns out that this closure of this linear span is bigger or smaller than compact?
Mm-hmm. Oh, bigger or smaller? So in which way because
what you would like to expect in general?
Yes,
something
in general,
W is not regular, then it turns out to be bigger or smaller.
I expected, I would okay. So maybe there are some experts that will correct me on that, but I also expect it to be smaller in general, not to have all compact operators.
Mm-hmm. Okay, this left-hand side is just a linear span. There is no reason for this to be an ideal, yes?
Yes, so there's something on the chat. So Adam Stasky is saying that there are examples both ways, that neither must hold. Okay.
Oh, okay. Okay, thank you.
Yeah, thank you. Okay, so this is a definition by Paschen-Skandalis, and what you can get from this. So you start with, here, this is why oh, there's a semi-regularity where we have just one containment. That's another comment by Adam. Thank you for that. So here, what I like about this approach is that we just have operators on Hilbert space, right? So there's nothing really abstract about this from the very beginning. Okay. And now an example from the, say, commutative world. If G is a locally compact group and H is, you take L2 of G, say with right invariant Hermitian, then this formula here, W on psi, defines a unitary operator on H tensor H. And this operator, one can check that this is a multiplicative unitary and also that it is regular. Okay, so if you start with a locally compact group, you will always end up with a multiplicative unitary that is regular. And then, well, I'll not go into like full details here, but this operator contains the full information about the group and its dual in the abelian case. So for example, because I'm not assuming that the group is abelian. So for example, here, you can get the C-star algebra of all continuous functions on G vanishing at infinity from W, just slicing it with those normal functionals. Okay, so that's one instance where you can actually recover from W the information about the group and the C-star algebras that you can associate with. Okay, so that's the example of a multiplicative unitary. And now, if you have a regular multiplicative unitary, you can prove that the following algebra, which is inspired by this example, okay, so it's exactly this. But now W does not come from any locally compact group. You start with a multiplicative unitary, and then this algebra, which I denote by AW, is as you get a separable C-star algebra. Okay, and moreover, there is a unique non-degenerate star homomorphism such that, and so this plays the role of the multiplication in the group, right? So this is the coproduct in your quantum group.
Mariusz, sorry, a stupid question. Is it obvious that this AW is an algebra?
Well, it depends what you mean by obvious, but it's...
Well, I mean, of course, I see that it's a vector space, right? That's obvious.
Sure.
But I cannot just verify it immediately in my mind that multiplication of two such elements is against such an element.
Well, that's true. And it's not, I wouldn't say it's immediate. Well, you have to check. Oh,
okay. Okay, using a convolution of the linear functions, it follows almost immediately. Okay, good. Thank you so much. Yes. Okay. So that just goes by convolution. Okay.
Okay, thanks for that comment. Oh, there's one more. Yeah, but still we have to use the multiplicative unitary. Okay.
Because you see, I remember something was far from obvious. So, but adjoint is far from obvious and sometimes wrong if a regularity is dropped. I remembered simply because I've seen these formulas zillions of times. And I remember that something was non-obvious. I just didn't remember what. So it's adjoint, which is non-obvious, but it's a star algebra. But that it is an algebra, it follows by, you know, convolution gimmick. Okay, thank you, guys.
Yes. Okay, so we have this, and that's the comultiplication satisfies this formula. Moreover, you have those the things that you, if you know the definition of a compact quantum group, where you get also this sort of left and right cancellation properties for the. Okay, so that's to get something more familiar. And if this C-star algebra is commutative, one can prove that it's actually it's equal to C0 of G for some locally compact group, and that's what Bash and Skandalis already proved. And of course, so for me, that's the definition of a regular locally compact quantum group. So a regular locally compact quantum group is a pair, this AW and delta W, which is given by a regular multiplicative unitary on H tensor H. Right, and I start with, so there's this God-given Hilbert space that I start with. And if W is understood, I'll omit the subscript and just write down G equals A delta. And just for the sake of completeness, Voronowicz introduced a property which is weaker than like a regularity and recovers all known examples. So there are examples of locally compact quantum groups that are not regular. However, for this talk and to have any sort of Stone-Neumann theorem, you have to assume at least regularity, and if not strong regularity. So there's this property called manageability that was introduced by Voronowicz, which is slightly more technical than regularity. However, all regular multiplicative unitaries are manageable, and I'll not go beyond regular locally compact quantum groups here in this talk. And now there was this question of Pontryagin duality. So if you start with a locally compact quantum group given by a multiplicative unitary, say regular or manageable, you define the dual as follows. You just define W bar here using the flip operator, and this is the W star. And this operator, you first prove, of course, that this is actually, again, a multiplicative unitary. If you start with a regular one, then you get a regular one. If you start with a manageable one, you get manageable, and again. And this way it fits into this definition of a locally compact quantum group in the sense of Voronowicz or Bastian-Skandalis. And then you can prove that G hat hat is, well, actually G again. Yeah, but this is not. And so what is important, of course, is that if the group that you start with is just, well, the classical locally compact abelian group, if you start with your C-star algebra of functions vanishing at infinity on your group, well, this dual quantum group would correspond to functions vanishing at infinity of the dual group, right? So we recover the usual Pontryagin duality in that case. Okay, but now, so let me go to, look, examples. So that you see that there are a lot of regular locally compact quantum groups. So first of all, I already told you that classical locally compact groups are regular. And here, so just for the sake of completeness, I wrote down that the co-multiplication is just given by the multiplication of the group. Then reduced group C-star algebras. Again, you can show that these are quantum groups coming from a multiplicative unitary, which is regular. And in fact, this is this first part of, even when your group is non-abelian, your dual is something that is kind of familiar still, because the dual group of C0 of G, you get the group C, reduced group C-star algebra of G. And then, of course, compact quantum groups of Voronowicz, which this class consists also of Q deformations of simply connected compact Lie groups, right? So this is also a very big class of examples, and they are all regular. Discrete quantum group, defined, well, introduced by Voronowicz and Podleś and by Van Dal.
Mariusz, can I ask you a naive question?
Sure.
Of course, when you apply this hat procedure, this quantum Pontryagin dual, as you argued, it's an idempotent, so G hat hat is G again. So now if I would apply a hat to this reduced C-star algebra of G, of course I would get again the C naught of G, right?
Yes.
But what if my group G is not amenable, and instead of reduced, I take the maximal? So C-star convolution, the maximum convolution C-star algebra of some non-amenable group. And now I apply this hat to it. So what will I get if not C naught of G?
Well, so that's, so quick answer would be, I don't know, but I think that if you even talk about, in this context, if you want to talk about universal, not only reduced, it's already if you define universal, and I will talk about the universal of the quantum group, already this would not, it's not always a quantum group. It is very close to being a quantum group, but it's not always a quantum group.
So you mean that if I would take the C-star max of G, then perhaps it wouldn't be of this form AW delta W, right?
Yes.
Okay.
But I'm like
Okay.
I said, my first answer would be I don't know, but that's my suspicion.
So this
Microphone.
this double hat probably is for abelian, right? It's not.
No, that's general. Mariusz can go back a few slides and show.
So this is the definition for any
In general Pontryagin duality. G hat hat is G. But where he states it's for just compact quantum groups that are of particular forms. I mean, locally compact quantum groups, AW delta W, and maybe I don't know, something is missing. I don't know. But when you said that it is manageable, then it covers all examples, so that's a bit confusing.
Well, so in the compact case, it should. I don't know the answer to what I will get if I start from the universal one, if the group is not amenable, but then it will be some other compact quantum group. So in the compact case, then yeah, sure.
The duality in this case is formulated using the reduced version because this multiplicative, well, wait a second. Because these multiplicative unitaries come from regular representations of quantum groups using the Harways, which are faithful on reduced versions, but not on other versions. Okay. I have a feeling I understand what's written, but I don't have a feeling I understand how it answers my question. But okay, let's carry on. It's not, I don't want to sort
once again, so I'd like to thank you for all those comments, because these are really helpful. As I said at the very beginning that this is still a new ground for me, but okay. Let's go further. So this slide was I just wanted to show you that there are a lot of examples. And the last class of examples are compact quantum groups. Well, not compact, but quantum groups coming from multiply Hopf algebras. Right. So there is this class of quantum groups that you can know that in the compact quantum case, you always have this dense Hopf star subalgebra, right? In the locally compact quantum group case, this might not be true, but there is still a class that when you start with something that's called a multiplier Hopf star algebra, and then starting from this, you get a locally compact quantum group in the sense of Voronovich or Pageant's conduct. And these are also regular. So that's another nice class to add to this list of examples. Okay, so representations. So
that's a quick question. Sure. For the Q deformations, what are the W's like? What are the constructions?
Unfortunately, I don't hear the question.
So for the Q deformations example, right? So how to realize this means your construction you explained in the slide. What are the W's like? Or what are the Hilbert spaces?
So I cannot hear the questions. That's
strange.
Yeah, so I know that you're using the mic, but I'm
using them.
Yeah, he cannot hear him online, is it?
I hear it, but it's not very clear. I just hear that someone is talking, but I cannot distinguish all the words.
So is it better now? Speak without mic.
Can you hear him now?
Well, still very, very vaguely.
I think, Mariusz, I think the question was about example of quantum of Q deformations, Q deformed quantum groups.
So Ludwig heard it, so that's.
Oh, okay. This I heard that was about Q deformations, but what about is it by how these examples are? How do they fit?
Yeah, exactly. Yeah, how do you get a W? Okay. I mean, you explained nicely how you get a W for any classical group, but
sure,
nice formula. So now the question is, okay, let's take SUQ2. How would the W look like? That's how I understand your question. Right? Okay, yeah.
That's how the W will look for
whatever. Say SUQ2.
SUQ2. Okay. So yeah. So that's. I might need to write some things down for this. Let me check how I can do this.
But I think this is Voronovich wrote this in somewhere in some explicit form, probably, no?
Oh, sure, yeah. You can. That could be my every answer, right? That Voronovich wrote it somewhere. Check it out. But I have my tablet with me, like a graphic tablet. So I'm trying just to connect it so I can write it down.
Okay. And there was also a question what the Hilbert space would be. I mean, classically, the Hilbert space is just L2G, right? So it's some
Sure.
form of.
So for the compact quantum group case, you take you have your Haar measure, and you take the GNS representation with respect to the Haar measure, and then you define W on that space. But you know what? I'm having some troubles with connecting this device, so maybe you can go.
By the way, if you type on chat, can you also speak? I mean, that's if you have a microphone, just please speak up. I mean,
Yes, exactly. Maybe
I can read it, but maybe.
So this is exactly what I said. So there's a comment here that you have Haar state. There's an explicit formula in any compact quantum group case.
Yeah.
And then you take the GNS construction with respect to that Haar state.
Yeah, that's what you said. Yeah.
And then W is the left or right regular representation with respect to that.
Okay.
Yeah, but sorry, I wanted to try this device and to write it down, but it's exactly what it's written here. So this is the right.
Probably we can continue. So then we
So you can do left, right. What I'm doing is the right regular representation. So this formula here would give you a right one.
And this paper by Bajen Skandalis, it seems to me it's ancient, right? It's been published like eons ago.
That's true. Do
you remember the year? 1980, 90, whatever.
I don't remember the exact year.
1993.
Okay, thank you. 1993. Okay, so I wasn't far off. Yeah.
So now we know those examples of regular in quantum groups. Let me go to representations and then to the theorem. How much time do I have still?
You have 43 minutes.
Oh, that's a lot of time. Okay, because I was starting to worry that I'm just so okay. Let's go ahead and I'll define the representations and we go from there. So this is just what. So this slide is about generalizing the strongly continuous representations of groups on Hilbert spaces, right? But now I'm in the non-commutative situation, so I have to distinguish between things on the left and things on the right. And that's why I define the left representation of G on a Hilbert space. And this is given by unitary in the multiplier algebra. Oh, so here A is this algebra of your quantum group, and then I look at representation on Hilbert space K. So I know this is maybe not the best choice that compact operators on K.
Well, you're doing KK theory this way.
Yeah. And this is the definition of the representation, which just generalizes the fact that usually one has just a homomorphism of groups, right, from G to bounded operators on K. So this is just how do you generalize it in this context using this Lac numbering notation. So that's the left representation, and the right representation is again unitary in this multiplier algebra, and it satisfies this equation. Okay. So first of all, and this is important for the next part of the talk, is that the multiplicative unitary W that is generating my locally compact quantum group is in fact a right representation of G on H, right? That's your multiplicative unitary equation. That's how the coproduct was defined. Let me go back. It's here, right? That's the equation that W satisfies. But if you look at it, well, if you now look at representations not of G, but on G hat, it turns out, and one can also show that W, the same W, is also a left representation of G hat on H. And that's important for in the few slides. That will be important. Okay. So now, this is something I already said, that in the classical locally compact group case, every right representation like this, it just gives you a strongly continuous unitary representation of your group on B of K, right? So this is how you generalize strongly continuous unitary representations to the context of locally compact quantum groups.
And what about left?
Oh, the left, right are the same in this context.
Okay.
But that's a good question. I don't know why I wrote down right. It's just left or right would give you the same in this case, because you see this isomorphism here. It's not important if I put G here or C of G here or here.
Yep.
Right?
Yep. Okay, I've got you.
So okay.
Okay,
So
I have a maybe stupid question.
Sure.
Is it always the same that if you take a multiplier algebra of compacts tensored with A, it's just the same as taking multiplier algebra of A and then tensoring with all B of Hilbert's
Oh,
phase, all bound?
There's no, I think.
No, I think it's so for sure. If you take multiplier of the tensor, of the tensor product, it's not the tensor product of multiplier algebras. That's for sure. No, and in most cases, probably no. Well, in many, and in particular here, I'm sure it's not the case. Oh, if A is, we get, so Adam wrote us an if and only if condition. If A is finite dimensional, so that would mean you have to start with a finite group, let's say, or a finite quantum group.
So in general, this multiplier algebra of the tensor product is larger, yes?
Mm-hmm.
Okay. Okay, thank you.
So let's go further. So, okay, representations. That was the representations. Now, the universal quantum group C-star algebra. So if you start, so that's something that Piotr was talking about for a second, because what we talk here when we use this multiplicative unitary is the reduced version. Okay, so we have the reduced version of your quantum group, and there's also a universal version. And I will not go into the details how to do this. I'll just state that if you start with a locally compact quantum group, then there is a maximal left representations of G hat on, well, a Hilbert space. And then you define your universal quantum group C-star algebra as follows. So it is maximal in the sense that you can write down a norm condition that for any other left representation of G hat, this one is, and if you slice appropriately with functionals, that you get something bigger in norm, right? And then this is how you define your universal quantum group. And a few things about that is that there is a co-multiplication. You can write down a delta U that would, oh, now here there is typo, should be AU again.
Mm-hmm.
So you can define a co-multiplication, and there's also a surjective map from AU to A. However, this AU delta U might not be a quantum group in the sense that it might not come from a manageable multiplicative unitary.
Okay.
Right? But it's pretty close to being a quantum group.
Already, this Hilbert space is separable, or it is something like a direct.
So here, yeah. So here it's a very big one. Yeah. You take, as usual, if you want to have something universal, you have to take a direct sum over.
So in the same spirit as in this construction, where you take all possible states or pure states, yes, and then
Yes.
take direct sum. Okay. Okay, thank you.
So here, what you actually, well, yeah, that's a similar idea, I would say. So what I want to talk about this universal group is that in particular, you can prove that left representations of G hat on a given Hilbert space are in one-to-one correspondence with non-degenerate star homomorphisms from AU to bounded operators on K. Right, so that's, if your group is abelian, right, if you had a locally compact abelian group, then there is no difference between non-degenerate star homomorphisms from your group C star algebra and representations of G hat. Right? And here the same holds, but only for this universal version. Okay, so we have the universal quantum group, and now we can slowly go to defining the Heisenberg pairs or the Heisenberg representations and Schrodinger representation. But first, I want to talk about the thing. If you look at the proof of Mackey's theorem that I showed you, there was this one point where you needed cross product, and you wanted this cross product, a certain cross product, to be isomorphic to compact operators on L2 of G. Right? So that's the part which is most troublesome in the world of locally compact quantum groups, because that world is much richer, and there will be some groups that will not satisfy this isomorphism. So we need to put it practically by hand to get the result. Okay, and that's this class of groups is called strongly regular, and I would like to go to that. But first, let me define what a full cross product, what I mean by a full cross product. I'll go quickly through that construction. So first, you have to have an action. So an action of a locally compact quantum group on a C star algebra B, say right action, is a non-degenerate star homomorphism alpha. And here you define your usual, you define it by your usual conditions. So one is co-associativity, right? So that's the first of the co-action condition. So here I write down action when it's an action of G, then there's this terminology that if the algebra co-acts, but the group acts. So that's might be pretty annoying, but that's the way to just makes sense out of all those symbols, right? So the group acts and the algebra co-acts. So we have this condition, and the next condition is, it was first formulated by Podleś. It's sometimes called continuity of the co-action or the continuity of action. And it's that if you take element of this form and you take the span and you close it in norm, you get all B tensor A. And so where A is your C star algebra of your quantum group. And if this is satisfied, we say that BGA is an right G dynamical system. Right? Sometimes some authors define, as you also add this additional assumption that the action is injective. However, there are some examples of non-injective actions that actually are important for this talk. So first of all, of course, this delta that defines is defined by your multiplicative unitary is an action of G on C0 on this C star algebra A, right? So this is an action of G on A. So this C star algebra of your group. Sometimes people use this suggestive notation that A is C0 of G, bold G, let's say. Then it will be maybe much easier to understand what I write here. However, this is the way you can. I guess it's still pretty clear what I mean.
Mm-hmm.
In the commutative case, so if I have commutative C star algebra, so B is C0 of X and A is C0 of G, we just get a notion of group action on the space. Right? That's exactly what we're generalizing here. And this is what is important is that G acts on this universal quantum group C star algebra, just using this reducing map lambda that I mentioned before, right? So on the right leg. So we end up in multipliers of B tensor A, not AU.
Okay.
So this is important that we have this action. So the GX.
By the way, Mariusz, maybe it's worth pointing out at this moment that the first blue dot is kind of obvious. It's associativity in the classical cases. X GG prime is X GG prime. But this one maybe is not so obvious when you first look at it. But it says that if you take the neutral element of your group and you act with it on any element in your space, it acts by identity. So XE is equal to X.
Yeah.
And it's not so obvious when you first look at it.
Yeah, thanks for that. Okay, so what's more? So
in Hove algebras, we would have co-unitality instead of.
Yes, exactly. And this would be, well, in the case of compact quantum groups, if you assume injectivity, then it would be probably equivalent to co-unitality.
Not quite, because you might have a simple C-star algebra which has no characters. So co-unitality sucks on the level of C-star algebras.
Oh, you're right. Okay,
Yeah.
thanks for that. Okay, so yes, that was.
That's why Podlesh invented it.
Yeah, sure. Okay. Okay. So now, as in the case of actions of groups on C-star algebras, well, this I also might have mentioned that this also generalizes the notion of an action of a group on a C-star algebra, right? If you start with a, not necessarily, if B is not commutative, but A is just C0 of G, then you get your, well, you can recover from this, your action of a group on the C-star algebra by automorphisms, by star automorphisms. Okay. So now we know that for C-star algebraic G-dynamical systems, there's an important notion of covariant representations, which then leads you to the cross-product algebras. So let me very quickly go through that as well, just for the sake of completeness. So in this context, if I have a locally compact quantum group and a right G-dynamical system, a covariant representation consists of first a non-degenerate star representations of the algebra B on which you act. And again, now I see that the use of the letter B was not maybe the best one.
Let it be.
Let it be, yeah, right. And then you take a right representation of G on K. And the compatibility condition is this, that pi tensor identity alpha of B is exactly U pi of A tensor 1 U star. Right, so and here, of course, so the thing with quantum groups, locally compact quantum groups, is that left or right actions, you get a different definition of covariant representation. So you have to just start with a, let's say, left or right action, and then just stick with it, because if you change, you get a different definition, and things are not so. So one of the biggest problems to write down the right definition of a Heisenberg representation or Schrodinger representation is to make sure that all your lefts and rights are in the right places, because that's one of the.
Mariusz, do you assume that A is equal to B?
Small a is equal to small b. Yes,
okay.
That's my assumption. So there's a typo here, exactly. I changed it just a few minutes before this talk to b's everywhere, and I was, well, prepared that there will be some typos. So that's one of them. So this should be small b, of course, because otherwise it doesn't make sense. Well, it makes some sense, but I don't know. So, and this small b is in your algebra B, right? In the domain of alpha. Okay, so that's the covariant representation. And of course, well, you can be more general also with, I should have said this when I defined the representations of quantum groups. Well, you can define representations on not only Hilbert spaces, but, well, say C-star algebras or even Hilbert modules over C-star algebras. And that's important for the next definition. Because if you start with a right dynamical system, you define a full cross product by some universal property. Then, of course, you show that it exists and it's unique up to star isomorphs. So your full cross product of a right dynamical system consists of a C-star algebra denoted as follows, right? By this cross. Maybe I should put a U for universal or for full cross product here, but I will not use any other cross product in this talk for C-star algebras. So sorry for that. So I take a C-star algebra and I take a covariant representation, which I denote by JAX, and which is universal in the following sense. So if I find any other covariant representation of this, oh, there's a lot of, yeah, so maybe I can use, maybe somehow I can try to. Oh, it works. Okay. So because there are many typos here, so I think I should just make this corrections. So otherwise it will be very hard to read. Okay, should be fine. So I take a covariant representation, of course, of the same dynamical system that I start with on the C-star algebra, such that this universality follows, right? That if I find any other covariant representation of this dynamical system on a different C-star algebra, then there is a unique non-degenerate star homomorphism from the C-star algebra that I have two multipliers of D, such that, and this is this universality property, right? That this JA is universal in the sense that there exists this pi cross product U, the star homomorphism, such that if I compose them, I get pi. And here from X, I can get U just by composing it with pi cross product U tensor identity. Okay, so that's the definition. And then, of course, you have to show that such a thing exists and that it's unique up to star isomorphism, right? And you can do it if you start from your right dynamical system. You can actually construct this thing, right? As usual, those definitions by universality. First, claim that you first write down this universality in the definition, then you show that it exists. Okay. So that's your full cross product. And you can see that if you look at cross product from this perspective, then it's at the beginning of my talk, I was talking about those Heisenberg representations, that they were pairs of representations satisfying some conditions. And you need full cross products to write down the Stone von Neumann theorem, because for reduced, you don't have this universal property. Okay. So yeah, so I'll just now erase my annotations and we'll go further. So the full cross products exist and it's unique up to star isomorphism. That's why I said already. Okay, now the strong regularity is the following definition. So the G is strongly regular if and only if this cross product is all the compact operators in H. Okay, so I start with a multiplicative unitary, which is, we can start with a regular one here. Because, well, it should give you some hint that strongly regular should be regular. That you start with a multiplicative unitary on H tensor H, then you define your universal quantum group algebra. You have this action that I told you about, and then you can form this universal, this full cross product, and you claim that this is by definition true. Okay, and the fact that you have to claim it is that, well, there are examples when this is not true, right? So you can have quantum groups in the sense of Voronowicz, so they will come from a manageable multiplicative unitary, but they will not be regular and they will not be strongly regular. So few facts is that strongly regular implies regular. All the examples I showed you of regular quantum groups are in fact strongly regular. So that's good, but you still have a lot of examples. And this is the question for the experts that already helped me a lot, but maybe they will agree to help me even more, because I don't know of any example of a strongly regular quantum group that is not regular. I don't know if that's known or not. So if you want, you can write down something in the chat or just say that.
I think the other way around, MARIUSZ. An example of regular.
No, sure, of course. Yeah, the other way around. Yeah. Yeah, otherwise there are two statements that are in contradiction with each other.
Yes.
Yeah, that are regular but not strongly regular. Yeah, thanks. Of course.
But let me guess, if you have a classical group, then it is not only regular but also strongly regular, right?
Yes.
Okay.
Okay, there's something in the chat.
Okay, Adam says that no such examples are known, so it's a subtle question. Okay, yeah,
yes.
wow.
So yes, that's but still the examples that I showed you are both regular, strongly regular. So that's and still a nice family of groups. So on one hand, of course, so we're slightly cheating in this approach to some fundamental theorem for locally compact quantum groups, right? Because we assume what we want to get in the end in this proof. So my idea is that maybe strong regularity would be equivalent to a version of Stone von Neumann theorem, and that would be interesting. But now I'll only go through the original, the modern proof of Mackey's theorem in the case of quantum groups, and that's probably my last slide. Oh, but first, so that's the whole. So okay, so up to now I was just talking about things that are well known for the experts, and they know it much better than I do. So one thing, when you look at Mackey's theorem and the definition of Heisenberg representations and the definition of Schrodinger representation, is that, well, you can try to do this for quantum groups and see what you get, right? And even in the literature, there are things that look slightly like Heisenberg representations. They are called Heisenberg pairs by Mayer, Roy, and Voronowicz. But still, well, if you find something in the literature, then please let me know. But I couldn't find anything that would be of this form that I'm about to present you. And this is basically, so in the joint work with Lukas, Leonard, and Jacek, we do much more than this. But here is just my reformulation it for this language of multiplicative unitaries, and the definitions that I think you don't have much choice. The definitions are already given, and you just look through literature, you crank the locally compact quantum group machinery, and you should get the Stone von Neumann theorems. And that's what I'm about to tell you. So first, I define a G hat G representation, and this would consist of a left representation of G hat on K and a right representation of G. So in the Mackey's definition, you just take two representations. One was a representation of G hat, and the other one was a representation of G. But here you have to make sure that you take care about left and right. That's the only addition. And the Heisenberg representation is defined as follows. So you take a G hat G representation, right? So V is a left representation of G hat, and U is a right representation of G. And you say that they satisfy this condition. And this should look like the pentagonal equation if I substitute W everywhere, right? That's the first hint. Because if you want to have your Schrodinger representation, this has to be just this pair, right? So the Schrodinger representation is a G hat G representation, W, W on H. So as I told you, your multiplicative unitary is a left representation of the dual group and a right representation of your group. So there's no other choice for Schrodinger representation, in my opinion. That it has to be this. And then,
sorry, Mariusz, but I'm confused. In this second definition, you have W all of a sudden, not neither U nor V?
Oh, W is, so I start with a locally compact quantum group that comes
AW. Okay. So you have so you have say regular or strongly regular multiplicative unitary W, and you have so that's the same W as at the top.
Yes, exactly. Yeah, thank you. So that's the same W. So so there's this W given. So I'm starting with a quantum group. So it has a multiplicative unitary. It is generated by some multiplicative unitary.
Yeah.
And here, I'm not assuming anything about regularity or stronger regularity. These symbols, these definitions make sense for any W.
Okay.
Right?
At least manageable.
Yeah, at least manageable. So I write down those definitions, and the first one, the Schrodinger definition, the representation definition is, in my opinion, that's the only thing you can take. Just left, it would correspond to left-right regular representations, which is it, and this is exactly the case in the classical Stone von Neumann theorem, right? When you write down the Schrodinger equation, or when you write down the operators, X and P. So that's your Schrodinger G hat G representation. It has to be this. And then you define Heisenberg representation. And of course, you define it in such a way that if you substitute W everywhere else, so let me maybe go to examples, right? So these are my definitions, and the examples that, well, might convince you or not, are that if I take a classical locally compact group, then any G hat G representation is just a pair of strongly continuous representations of G hat and G. And then the condition defining the Heisenberg G representation is, well, the condition that you want. Is V of chi UG. And here this W was, that's why of course, this is just a number. I could put it at the end. I put it in the middle, just you can see that it stands where W was.
Okay.
So this is because I wrote down this operator W as using multiplication, right? But in the end, this W, it has all the information about your group, and it gives you just the pairing, right? It's a multiplier on it. You can think about it as a multiplier on C0 of G hat tends to C0 of G. So, and if you, in the classical case, if you evaluate at a character in G, well, the only thing it can be, if all the theory is right, it should be chi of G. Right? So that's how you get this part. And this is just your definition of V and U. And then this equation, this vile form of the canonical commutation relation, is exactly the equation I write here, right? So that's that. And then another, well, just to this simple observation that I made already, that if you, this Schrodinger G hat G representation is an example of a Heisenberg representation, And then the condition of being Heisenberg is simply the pentagonal equation, right, of your multiplicative unit. So the whole idea of this project was to write down the definitions in the way that are, well, that these two facts would be satisfied, right? Because that's what you really want to get the Stonfeld-Neumann theorem. And then, well, I wrote down only my name here, but of course it's based on joint work. But in this form, I didn't want them to sign their names under something they did not approve. So that's why it's here.
Okay.
So if you assume to have a G strongly regular locally compact quantum group with a multiplicative unitary in a separable Hilbert space, then every Heisenberg G representation is a multiple of the Schrodinger representation. And the proof is exactly the same. So first you have to show that there's one-to-one correspondence between those Heisenberg G representations and non-degenerate star representations of the full cross product. And this is, well, it's not so straightforward. It is, you have to do some calculations. Of course, everything depends on the definition that you get. If you have the right definition, the calculations will be easier. So it took me a while to get this right definition, but then if you just crank the machinery and you try to prove this result, you get it after a few pages of calculations. It's not that hard. Okay, so, and that's how you go through this proof. The proof in the case of a locally compact abelian groups, you mimic everything for locally compact quantum groups. And this is true even if your group is not strongly regular, right? So this dot in the proof, so you don't need a strong regularity to prove that. Where you actually need strong regularity is this, right? Because if you now know that all Heisenberg representations corresponds to representations of the full cross product, then if you know that the cross product is just compact operators, well, then on the nose you get that. So first of all, you look at this isomorphism and you put your Schrodinger representation. So you get your Schrodinger representation through that isomorphism. There's an explicit formula for the isomorphism if you want. And if you put your Schrodinger, it would correspond to the identity representation on the compact operators, right? Just because you have the compact operators in Hilbert space and you want to represent it on the same Hilbert space, then you can just take the identity. So that's where Schrodinger comes to this. And then every other Heisenberg representation would correspond to some star representation of compact operators, which is a direct sum, a multiple of this identity, this representation given by the identity. Right, so that's basically it. And in the end, this so it might feel like so anyway. So this is, in my opinion, maybe I'm wrong, but in my opinion, this is how far you can go with this Mackey theorem. So you have your theorem, Stonfeld-Neumann, well, Mackey-Stonfeld-Neumann theorem. You want to generalize it for quantum groups, and I think for quantum groups that are not strongly regular, this will not be true. I don't know it for sure, but this should probably be true. So your assumption is, so your definition of strong regularity, I think, should be equivalent to this form of the Stonfeld-Neumann theorem. But this is still work in progress. However, it really generalizes the known thing. And as I said already, for me, it seems that this should have been done years ago, like in 93 was the Pasch, so probably that it should be done by then, more or less. But I couldn't find it anywhere, and it's not, and as I said, it was a great material to learn about locally compact quantum groups, because you just crank the machinery that you already have in all those great papers of Bornowicz, Vass, Ostermans, and all that, and you get the result if you have a smart choice of the definition. you can of course make your life miserable if you choose the wrong definition, which would be equivalent but not as nice, right? So that's the main contribution to that I think is interesting for that. And yeah, so I guess that was it. Thank you for listening. And this is a gnome that stands in front of the Institute of Mathematics in Wrocław. So, yeah, it learns algebra, analysis, and noncommutative geometry, of course.
Of course.
Yeah, thanks.
Okay, thank you very much, Mariusz. Now let's begin with questions. So, any questions from Trieste? No? Questions from Kraków? Adam?
Maybe one question. So if we could go back to this first classical case of this Stone von Neumann theorem. So
yeah,
you stated for Rn, yes? For the action of Rn.
Yes, this is just for two unitary representations of Rn.
And somehow in your talk, nowhere the Heisenberg group is somehow absent in all this talk. So is there any generalization of this classical Heisenberg group, which is like a R to the power 2n plus 1 with this?
Yes, that's a good question. So I was thinking about this, and of course, if you look at the classical Stone von Neumann theorem, you can see that this is actually a theorem of representations of the Heisenberg group, right? But what Mackie did is he said that I start with any group. So in a sense, you're defining Heisenberg group for a group or whatever. So it's not exactly so if you can generalize Heisenberg group. Let's say you can do maybe some good deformation or get a quantum Heisenberg group, right? And that would be something different than I'm trying to talk here. That's what I think. And this is also a different approach would be to just look at the C-star algebra generated, right, by this relation, and look at the representations of that C-star algebra, and that would be also something different. So what my understanding is that what Mackie did is that he looked at this and he said this is not about Rn, this is about a locally compact abelian group and its dual.
Yeah.
So you start with locally compact abelian and its dual, and then you're defining what's Heisenberg representation or a version of Heisenberg representation is for this. And then the Schrodinger representation is well, you know what you want for your Schrodinger representation on a group, right? You take the right regular representation and you take this mod. And in the locally compact quantum group case, it was also an easy choice, right? You use your multiplicative unitary that defines everything, just put it in both places as a left and right representation. You just use everything that you have for locally compact quantum groups. And then this Stone von Neumann theorem for locally compact quantum groups is that you start with any locally compact quantum group that's strongly irregular, then you get this theorem. I don't know a definition of a Heisenberg group associated to a locally compact quantum group. This would be something like this. I don't know what kind of an object would that be, or if it makes sense.
Well, I think can you hear me?
Yes.
Well, so I think in Mikey's formulation it's not about the local, just abelian, like commutativity doesn't matter. So just take the local compact group. So this Heisenberg relation, like in Mikey's language, or even in Weaver, they call it covariant pair. Is you start with a representation of G, and some representation of functions with C0 of G. Like they fulfill this similar this Heisenberg relation. So and then
yes, exactly. I agree that in the Mackey formulation, the fact that you take an abelian group is not important. That's true. It just, if you have an abelian group, then it's just much, you can write it very nicely, right? You have G and G hat, and then you have the symmetry. It's very symmetric, it's very nice. But in the end, as I also showed you, now you can take any locally compact group. You can even take any locally compact quantum group that's strongly regular, and everything works. So abelianity of the group does not matter in that formulation at all.
Yeah.
So then Mikey's motivation, I think, it's about induced representations. So, so could you go back to the last slide? So I just asked them.
Sure.
Well, the last one is one with no.
So of course there is a.
Okay, so I think what's Mikey theorem for induced representation is, if you look at the last line, right? So and then so Mikey's theorem, so it's about induced representation. So you have so suppose you have a subgroup of your bigger group G, right? So in last line, you can replace the C0 of G by the C0 of G mod H. Okay. So and then you take cross product with G, and then the right hand side will be the not isomorphism, but the Morita equivalence to the C star algebra of H. So in this case, exactly. if you take H to be the trivial, right? So and then the C star of H is just the one, by generating one, which is Morita equivalent to the compact object in this case. So and then I think this way I think he kind of answered like what are the induced representations. I think it's
exactly. But this is this part is well known in the locally compact quantum group case as well. So, so the induced representation and the theorem that the Green's impermittivity theorems, this was all done by Voss. So this is all well known. However, this particular formulation and this particular result, I was not able to find it in any reference, and we actually asked Voss about this, and he said, well, this should be true, this should be easy, but he didn't know. So this is, I'm just, this is the first seminar of the academic year, so that was just a very light talk about some result that we were able to get. I'm not saying this is, it should have been done many years ago, right? So that's for starters, and it wasn't, if you do everything right, but this was the part, this was the most of our work was to just get the right definition, and it's hard to appreciate if you just see the definition and it all follows smoothly, right? But to find this right definition and find the right framework, and to that was really painful, and you have to make sure that's left and right, and you have the opposite group, you have the commutant group, and so it's really a nightmare in this world of locally compact quantum groups, and that I had to learn the hard way. And so but if you go through that and you write down the right definition, then everything works smoothly, and the result is, well, pretty much straightforward. Well, from the hand side.
Okay.
And it's really, yes, it's just this is really a generalization of Mackey theorem. You can go even further. This is what I wanted to say. Last comment. You can, instead of representations on Hilbert spaces, you can take Hilbert modules over elementary C-star algebras on which this quantum group acts, and then you get the same result, which is a generalization in both directions now. So you can, instead of Hilbert space representation, you can generalize it to Hilbert modules over elementary C-star algebras, or even maybe, and this is a project that is in progress, that's what Lucas Hall is working on, to get rid of elementary, maybe to use type 1 I don't know about that, but it's just, you can still do things. But if you just want to generalize Mackey theorem, as it was stated for Hilbert space representations, this is how far you can go. This is the and this is the contribution of this talk.
Okay, we have a question from Warsaw.
I have a question coming back to contracting duality. Next, this contracting duality is used in the Heisenberg representation in the classical case. So my question is about the fact that is related to the fact that this classical contracting duality can be rephrased entirely in terms of irreducible representations of abelian groups, which are one-dimensional. So these are homomorphisms into U1.
Sure.
Next, you are changing the language. Your language is about these multiplicative unitaries, but still you can speak about representations.
Yes.
So my question is, how to what is happening to irreducibility of this representation from the contracting duality in terms of this multiplicative unitary? Because on this level, there is no anything about decomposition into irreducible representations, for instance. So
in the end, yeah. I know. So in the end, it's this decomposition into irreducible representations. It's all in this fact that I work over strongly regular groups in the end. Right? So I only look at my Heisenberg representations are in one-to-one correspondence with representations of compact operators.
I see.
And for compact operators, I know that every representation decomposes as irreducibles, right? And
okay, thank you. It's a good explanation. Thank you.
Okay, anybody else? Any further questions? Any questions from Molpakone, Ludwig? No?
No, it's okay, except that, okay, many people had this knowledge of this facts, but nobody, it's nice that someone combined with all this and used the right definitions to define this, to get this result. Okay, so congratulations.
Okay, so Ludwig is happy. All right, if there are no further questions, I don't see any hands raised. Okay, so let's thank Mariusz again for a very interesting semester and academic year opener. Thank you so much, Mariusz.
thank you.
So let me stop recording.